If you go back to studying your first integrals, you remember that most integrals are not directly solvable. You can't just look at it and say, boom, I found know the antiderivative. One of the things we have to do is use substitution. That's kind of what I call the bread and butter of dealing with integrals. Most of the time you're gonna look at that and go, I kind of get this. I'm gonna have to make a substitution though to make this work. Well, what we find is that there's an analogous structure for using in double integrals. But before we do that, let's review a little bit about why this or how this works in a one-dimensional space. So if we have a standard function from a to b, we can define u in terms of x with this function. We can say x is equal to some function of u, and then we know that dx is the derivative of that function times du. We use that sort of almost as a shorthand terminology, but it's a result of the chain rule, right? Because instead of having this integral, we plug in that function of u wherever we see an x, and then we replace dx with the derivative of g, and then we have du. So in doing this, we also develop new limits where c is related, or the new u limit is related to the original x limit, and top and bottom through the function we've defined. And so you might say to yourself, well, how do we do this for double integrals? And we've seen that we could do this with iterated integrals, but whenever we were doing this with iterated integrals, our substitutions were still integral specific. So the question kind of might arise, how do we describe substitutions in double integral form? How do we do this? And the answer is with this process here. So if I have some sort of region R, and there's a function that I'm integrating over that region, I can instead define some sort of alternate region, similar to the way that this went from A to B, but the limits changed from, there was this two numbers, and it might have changed to these two numbers or these two numbers, right? There was some sort of change of the domain for the integral. Domain's not really there, but think of it, limits of integration. Similarly, we change the region, and instead of substituting in a single function or a function of a single variable, we now have two functions because we have two variables, and each of them are functions of multiple variables. But on top of that, we end up with this j function. And this right here is an absolute value, not to be confused with what we're going to see in the coming sections. So this is an absolute value of this, which is a generalization of what you're doing here. Instead of this little g prime term, you end up with this j term. And this is what's called the Jacobian. So the Jacobian is defined as the partial of x with respect to u, the partial of y with respect to v. Those are multiplied, subtracting the partial of y with respect to u times the partial of x with respect to v. Now, in doing that, what we end up doing is creating a relationship of how these partial derivatives interact with one another. And by defining these functions, these substitution functions, in here we get this relationship and we get this little constant. And we're going to talk a little bit more about Jacobians, but before we do, I just want to mention that this is a method that's not limited to double integrals. We can use this exact methodology for functions of 3 variables, for 4, 5. Now it gets more complicated as we do this, but that's kind of the methodology. And we'll talk more about Jacobians in the upcoming sections.